Hey y'all, welcome to assignment number 13, continuity. Yes, I changed my hair up a little bit. I dyed it purple even though I don't think you can really see it. As we move into these next 2 weeks of AP testing, just want to give you some encouragement. You've got this. It might feel like you're working for nothing, but just know that you are working towards something and you have a lot of people rooting for you. And even if you don't, please know that you know that I am. And if you ever need anything, you have any questions, you need any support, I've got your back. And just keep it up. All you got to do right now is to keep going. I'm sure you'll hear more encouragement from me in other ways. As another form of encouragement, I'm also shortening assignments a little bit. So Tuesday's assignment is going to be pretty much our classic 30-minute length. On Thursday, I'm going to make a review assignment and then just make an exit ticket. All right, so let's jump in. So these 3 Delta Math sections for this assignment are 1, finding positive and negative domains, which you've already done. 2, types of discontinuities, which you should have done last assignment on Thursday's assignment. And then 3 is what we're doing today, is called continuity. So with finding positive and negative domains, I found a lot of mistakes in confusing increasing with positive and decreasing with negative. So increasing and decreasing is about the behavior of the function. So increasing is x increases, your y increases, right? Decreasing is as your x increases, right? Your y will decrease, it'll go down. Positive and negative is straight up just about location. So positive is anything where the y is above 0, and negative is anything where the y is below 0. So in this left-hand graph, you see that it's an increasing function as x increases, y increases, but there's different positive and negative domains. This function is negative, right? It's below the x-axis until x equals -5. Then the positive domain would be from -5 all the way up to 9 or 10, past 9. If there were arrows, it would be to infinity. Now looking at this absolute value function on the right-hand side, there's a decreasing piece and an increasing piece, but this whole function is a positive function because the whole function is above the x-axis. So that is the difference between positive and increasing. So increasing, decreasing, once again, is about behavior, how it's changing as output changes, whereas positive and negative domains is literally about the location of the function itself. Moving on to types of discontinuities. So this is literally, I went over it very in depth on the last assignment video. So if you're really confused, please check out video number 12. If you are having trouble accessing Edpuzzle, I've linked on the classwork page the YouTube page that I also upload everything on. So go ahead and check it out. It's labeled exactly the same. You should be able to find it. Let's do our weekly CFU right here, and this is over types of discontinuities. So check your notes, look at the last video, answer this question for a chance to opt out of a single Delta Math section. So it's easier to define continuity now that we've already defined discontinuity. So I actually have to take my little picture away. So here are 4 examples of graphs, right? And I've labeled them as whether they're continuous or discontinuous. So take a second before we talk about why, which ones are discontinuous and continuous, and look for some pattern. You might have said, right, these continuous functions, there's no point at which it stops, right? It just keeps on going. But whereas these discontinuous ones, while as they're going, right, it still keeps on going, but there's a gap. So we're going to talk about a couple of different ways to look at continuity. The formal definition of continuity is to guarantee it, when you look at the boundary of the domain, the function output must approach the same value from the left and right side as the input approaches that boundary. So anytime you hear left and right side, your brain should start moving towards the idea of limits, which we're going to review today. So in this case, right, if I said at x equals -1 for this left-hand side graph, what would the output be at x equals -1? You see that it's approaching the same value on both sides. The y would be -2. Same with your absolute value function right here. If I said, what is my output at x equals 2, you could see that from both sides, this function is approaching the same value. That means that, yes, check, these are continuous graphs. Now let's use the same formal definition to see why these are not continuous. So if you look at this left-hand side graph, if I ask you for what x equals 0 is, you have no answer, right? That means that this function does not keep going. It doesn't approach the same value from both sides. On this right-hand side, right, from the left side, if we're looking at x equals 1, from the left side, the function would be approaching -2, and so would it be from the right side. They're both approaching -2. The line is approaching -2 at that value. But the actual output is completely different. It's a whole different place. That's why it's not continuous. Now let's think about it in terms of limits. So this is a fancy way to break down how limits are presented. Let's break it down real quick. So the limit as x approaches a is any value on the x-axis. So it could be 5, it could be 25, it could be -30. As x approaches any particular value, this is the function. What is the y value that it's getting closer to? So I just want you to see exactly what the notation would be. You don't actually need to put that into Delta Math for this section, but it is very important to start getting familiar with the notation of limits as you move in calculus concepts. So from the perspective of limits, a function is continuous if the limit approaches the output values. So what that means, right, because that looks like a bunch of gibberish, is basically what I had said earlier from the left and the right-hand side. So this is the notation from the right-hand side, because from the right is a positive side. And as you approach it from the negative side, a negative, it needs to approach the same value, L. The output has to be the same in order for it to be continuous. So what you are actually doing on Delta Math is you are given a piecewise function, and you are going to use this concept of left and right-hand side to determine whether it is continuous or not. So another way to think about limits is you hear me say from the left and the right-hand side a lot, right? So basically think about it as like a fist bump, right? If someone comes in to give you a fist bump, you have to meet them where they're at. A limit exists if you meet them right where they are at. So when you're thinking about a function, when you're going from, the left side to the right side, you want those functions to meet at the same place from both sides, or else that's a lame fist bump, right? Like if you fist bump someone and they meet you right here, they don't pass the vibe check, right? So that is the basic concept of a limit. So this is the first example that we're going to talk about. This is a screenshot of exactly what your Delta Math is going to look like. You are given a piecewise function, and it's asking you whether it's going to be continuous or discontinuous. It's asking whether the function is continuous at x equals 2. So this is our given x value. So we want to see that as we approach from the right and the left-hand side, will it be approaching the same y value or the same output? The only way to find that out algebraically is to plug the 2 into both functions and see if they equal the same thing. So let's start with the right-hand side. So when we plug in 2 into this function, let's see what we get. So anywhere there's an x, I'm just going to input a 2. So 20 plus 2 squared, right? If you simplify that, you get 20 plus 4, which is 24. So we see that from the right-hand side, right? I'm going to put a little plus because that's from the right-hand side. It's approaching 24. Now let's see what's going to happen as we approach it from the left-hand side. So this is 20 plus, you're plugging in the same value 2. And so you see that you get 20 plus 4 again, which is 24. Meaning that from the left and the right-hand side, your value is approaching the same number 24. So if they're both approaching 24, then this is continuous. So you would select continuous for the answer for this specific problem. All right, so now that we've figured out example 1, now let's talk about example 2. Given input value is 3, and we want to see whether our outputs are going to equal the same thing on both sides. So you see that at x is greater or equal to 3,
right? Notice how this problem, the problem before, had one that was inclusive. You might not always see that. So at x is greater than or equal to 3, that means from the right-hand side, this is the function that we want to plug in. So 7 minus 2 times 3 squared, right? So I just plugged in the input in there, and so we're going to just keep on simplifying that. 7 minus 2 times 9, and then you're going to keep on 7 minus 18, which gives you negative 11. So you see that from the right-hand side, your answer is negative 11. Now let's see what happens on the left-hand side. So we have negative 6 minus x, so I'm going to plug in 3 into the x value. So negative 6 minus 3 is negative 9. So you see that from the left-hand side, it's approaching negative 9, but on the right-hand side, it's approaching negative 11, right? It's confusing because I'm on opposite sides of the paper, but I'm talking about this is from the right-hand side of 3, and this is from the left-hand side of 3. And so because they are approaching different output values, this function is discontinuous at x equals 3. So if they don't equal, if the outputs don't equal the same thing, then it would be discontinuous.
So those first two examples are the more math heavy ones. Sometimes when you get these problems, you might not even need to do any math. So for example, for this one, you have a function, right, at x equals negative 4. At x equals negative 4, you don't even have an inclusive point. You don't have a point. There is no function at exactly negative 4. So by default, you already know that this function is not continuous because there is no inclusive value at all. Now this one's kind of tricky. It's like it plays a little trick with your eyes. At x equals negative 4, right? At x equals negative 4, but with our piecewise functions domain, you see that the change occurs at 4. So at negative 4, you're at a point that's x is less than 4. And so you know that if you plug negative 4 in, you'll just get a regular continuous value. So you will automatically know that this value is continuous because the change isn't occurring at this given x value. I hope that helps.